Here. So we're just starting the recording, and with that I would like to welcome and to thank Manolis Georgoulis from the University of Athens to spend his valuable free time, as I heard today, and give a very interesting talk on solar stellar eruptions. Just to shortly introduce you to Manolis, so he's currently at the University of Athens, and he graduated from University of Thessaloniki in '93, and was at the JPL, Applied Physics Laboratory of Johns Hopkins University for a postdoc research in Maryland, and also was a senior professional staff there. And then he returned to Europe and to Athens in 2012, where he held a senior researcher position since then. Manolis is a very well acknowledged colleague of us in solar and heliospheric physics, and it was always a pleasure meeting you at conferences, because you always came with very new and interesting results. So it was always very exciting to follow your work, and it still is. And that's why I'm also very excited about this talk now, to hear more about solar stellar eruptions and planetary forcing. And with that, I would like to ask you, the floor is yours, and please go ahead.
Thank you so much, Manuela. Thank you for the kind introduction. I also enjoy very much the fact that I am standing in front of you virtually and giving this presentation. Thank you also for being here this late in the year, within the summer, in the heart of summer. Following this, I will try to be as encompassing and as understandable as possible. Just a minor correction. I am not at the University of Athens. I am at the Academy of Athens.
Academy of Athens, right?
Yes, but this is in the sense that Academy of Athens is a research institution, not a university. But other than that, we are just, a couple of kilometers away from the University of Athens, so it's not that far. So what I will try to talk today is just summarize recent work with Spiros Patourakos and Evangelia Samarade. It would not have been possible without their crucial contribution in this respect. So what I will try to do, and I hope I do it right, is to summarize the results of this work that we think holds promise as to the overall thematology of the Sun as a star. What do we know about the Sun, and how can we meaningfully extend this into what we know about other stars, and how can we make progress by this knowledge? So I'm going to try to pitch in by a question, a provocative question: what happened to Mars? And you can see over here in the background a pretty dry, arid Martian landscape that is supposed to be a riverbed. A riverbed meaning that at some point, perhaps billions of years ago, there was liquid water flowing on the surface. So how was this water, and how was the overlying atmosphere of Mars lost? Then I will try to give you a picture. This is a rhetorical question because I'm going to be focusing on one particularly likely answer. I mean, we are not sure yet, it appears, but this is a pretty credible answer. And I'm going to be emphasizing on this, which is the planetary forcing of stellar magnetic activity. And I'm going to go back to the Sun, try to extend some estimates from the Sun into stars, and then even go on, and this is our most recent work with Evangelia Samara, on a criterion for atmospheric sustainability of exoplanets due to the stellar magnetic activity. And finally, I will conclude and give some, at least in my mind, promising future extensions of this kind of work and this kind of reasoning. So I'm going to start with a video that was made, that was based on the results of recent results by NASA's MAVEN mission, that seems to be confirming, as I said, as it writes over there, what we suspected all along, namely that the Martian atmosphere has been lost because of the solar magnetic activity and because of ion escape, ionization and escape from the atmosphere, a process that we call atmospheric erosion. So this is the souring of Mars by the solar wind, eruptive or quiescent, but mostly eruptive. And if you have intensive magnetic activity from the sun that results in interplanetary coronal mass ejections, then you compress the atmosphere, in which case you ionize otherwise neutral atoms into ions that then follow the magnetic field lines that sweep the local space. They abandon the atmosphere and they are lost in deep space. So that's pretty much what we mean by atmospheric erosion, and the question is why it happens, right? So in trying to look more about this, when we started working on this topic, I was fascinated by this 1930, almost a century ago, article by Chapman and Ferraro. The solar wind was not invented, was not proposed by then. Until then, it was not until 1958 that Parker proposed the solar wind. So what you have here is a new theory of magnetic storms, as Chapman and Ferraro put it. This is Earth, and this is stream of charged particles. So if you have a front propagating into deep space, a front of plasma, then what you have is a magnetic pressure, in case there is some magnetic field background in there. You have a ramp pressure that has to do with the density of the plasma and the speed of propagation, and you have a thermal pressure that has to do mainly with temperature and the number density of the plasma. So if you have an unperturbed magnetosphere of a planet or anybody that has a magnetosphere, and you have a vacuum, you're going to have the magnetosphere extending up to a certain point. If there is no vacuum, if there is a wind, a stellar wind or the solar wind in this respect, then you're going to have the magnetosphere settling at a so-called unperturbed magnetopause distance that relates on the balance between the planetary pressure, which is mostly magnetic pressure, not that much thermal because it goes well beyond the planet itself, and it has to somehow balance the incoming pressure by the transient that propagates in the heliosphere or in the astrosphere. So in this respect, if you have a magnetopause distance and you take the simplest possible case, in which case you have a magnetic pressure by the interplanetary coronal mass ejection, and you have a magnetic pressure by the planet itself, based on this magnetospheric distance, this flows out by the analysis of Chapman and Ferraro. Then you have a situation like that. And the plasma pose distance, the magnetopause distance, is going to be at that point that the two pressure terms are being balanced. And then we had more recent works that were talking about a conceptual threshold of two planetary radii of magnetopause distance as the minimum threshold in which you avoid atmospheric erosion because of magnetic activity. So if you have a magnetospheric compression that goes beyond, that compresses the magnetosphere beyond the two planetary radii, according to a number of effects and mechanisms, you're going to have an enhanced ionization of neutral atoms in the atmosphere, the generation of ions that are going to be picked up by the magnetic field lines and be lost in space. Okay? So, back to the sun. We know that the sun erupts. We know that above the photosphere, you have the magnetic field taking over the evolution. and it gives not only flares, which are enhancements of the electromagnetic spectrum, but also coronal mass ejections that are ejections of plasma from the magnetized solar corona. Now, if you look closer, this is something that we know pretty well. There is a lot of twist, writhe, and linkage, I would say, in those magnetic structures that are being ejected away as coronal mass ejections, as CMEs. So the discussion about helicity came into play in solar physics and solar eruptions several decades ago. And here you can see some observations from a ground-based coronagraph in Hawaii that clearly shows coronal mass ejections. These are, 40-year-old observations, and they clearly show indications of helicity overall, well before space-based coronagraphs were commissioned. So magnetic helicity is pretty common in the solar atmosphere. What is helicity? Helicity is a concept of a very rich and enhanced theoretical background. When you have a closed volume, when you see a medium and you see the entire extent of the medium, then it is easier to define helicity based on how the two structures that you see over here, magnetic structures apparently, are being linked. Helicity also relies on the handedness, on the rotation pattern, and it could be a positive helicity, meaning a clockwise rotation, or a negative helicity, meaning a counterclockwise rotation. Well, in the sun, we have a slightly more complicated situation in the sense that we have an open volume. Magnetic structures are being penetrating through the photospheric surface we cannot see below the photosphere, and they are extending into the atmosphere. In this respect, this formula over here does not have a physical meaning in the sense that it is gauge dependent, so it's not unique. And in order to make it unique, we have the concept of relative magnetic helicity has been proposed, in which case it is the helicity relative to the current free or the vacuum magnetic field, the so-called potential field that is there if there is no plasma at all. If there are plasma, meaning electric currents, meaning moving charged particles, then you have a helicity which is non-zero, a relative helicity which is non-zero above the potential field, as well as a free current carrying energy. So more qualitatively, this is a model by B. Labet back in 2007, in which it shows a pretty complicated situation of the quiet sun, I believe. This is the modeled photospheric boundary, and you see clearly a lot of twist, writhe as well. You see this interconnectedness, so there is significant and very complicated linkage in there. It is a helical structure, even in the quiet sun. Then what you see on your left is a well-known movie by Bernhard Torok and by Tibor Torok and Bernhard Klim, in which case you see a failed eruption, and you can see helicity being present over here as well. The eruption was failed, but the helicity is there. So all in all, if you have a discrete bunch of loops penetrating above the photosphere, then what you have in this respect is a matrix of helicity terms. Each of these elements of the matrix can be positive or negative, meaning right-handed or left-handed respectively, and you have a very well-defined physical meaning if you have interactions in there. The diagonal elements of this matrix are the self terms of helicity corresponding to twist and writhe, whereas the off-diagonal terms correspond to the interaction between the different elementary flux tubes in there and are called collectively mutual helicity. So you have linkage and inductive effects in there. So a fundamental property of magnetic helicity that we know for several decades as well, but has been reaffirmed and confirmed, I would say, recently, is that helicity is conserved. Magnetic helicity is conserved contrary to the free energy. And this conservation has bounds. The dissipation of magnetic helicity is inversely proportional to the square root of the magnetic Reynolds number. That magnetic Reynolds number in the solar corona has units that has values that are substantial, well above unity of the order 10 to the 12 or 10 to the 11th or so, simply because the resistivity in the solar corona is so small in a magnetically dominated plasma environment. So if you have a highly conductive coronal plasma, you have a high magnetic Reynolds number, and this leads conceptually to the conservation of helicity, even in case you have short departures from this situation, which are cases of magnetic reconnection. Excuse me. If you have magnetic reconnection, then you have helicity approximately conserved. If you do not have reconnection, then helicity is going to be almost precisely conserved, and it's going to just be transferred from smaller scales to higher scales, to larger scales, in an inverse cascade type of evolution. So this creates another problem. It tells you that you do not have, where to put this helicity, as the sun, over a magnetic revolution of billions of years, accumulates helicity in its corona. It releases energy, but helicity stays there. And one has to be able to solve this apparent paradox, this paradoxical kind of evolution in which you have a finite free energy but an infinite magnetic helicity. You have, in essence, you have the helicity annihilation mechanism, which means that structures of opposite helicity might cancel helicity and end up in a mutually non-helical kind of resultant structure. But you do not have this happening because you have different flux systems overall that stay away from each other. And moreover, we have seen for a number of decades now that we have a statistical prevalence of one sign of helicity in the one hemisphere of the sun and another on the other hemisphere that is independent of the solar cycle. So if you have nothing to do with helicity, you're going to have it accumulating over there. And perhaps the only viable way to avoid this paradox is to have ejections, bodily ejections from the solar corona that carry helicity away. And these ejections are nothing but coronal mass ejections. So it has been proposed since the 90s that the coronal mass ejections are not a luxury for the sun or are not some exotic characteristic of the sun. It is a necessity. It is a necessity for the sun to be able to get rid of this helicity. Right. So how do we calculate this helicity? This relative helicity. I showed you before that you have some classical volume formulas. If you have the magnetic field structure above the photosphere, the three-dimensional magnetic field vector, then you can use these formulas. But as we all know, magnetic field can hardly be measured above the solar photosphere. So we do not have this three-dimensional magnetic field structure. And there are several efforts to work on this by using magnetic field extrapolations or by using modeling that gives us this three-dimensional structure and therefore the helicity. But these are relatively heavy calculations based on the sophistication. For example, even nonlinear force-free extrapolations cannot really be applied in real time if we wanted to do it in a pretty practical way on a large number of data, unless you severely decrease the spatial resolution, which in some cases works, in some cases it is not appropriate for the work we are doing. So what we aim to do was to try to find something that can help us estimate helicity in a pretty practical way. So what we did was having a situation like that, what you see on your left, which is a continuous flux function in the photosphere. What we did was that we first partitioned, we first segregated different patches of flux, positive or negative, positive polarity or negative polarity, so that to create this continuous to transform this continuous situation into a discrete kind of situation. And then we did a modeled connectivity analysis between these flux patches, which are now discrete, aiming to find out how much of the flux, how the different flux contents are being distributed between different connections, stepping, of course, on the flux conservation property. We did our analysis. I'm not going to give you the details, but you can read these papers over here, and then you can find both a linear and a nonlinear force-free approximation of the free energy, namely the energy above the potential field energy that is due to the existence of plasma, and the respective magnetic helicity, both in the linear force-free approximation, which is simple, and the nonlinear force-free approximation, which is kind of more realistic or perhaps more elaborate, if not realistic, compared to the linear force-free approximation. And then we put it to work. So we tried an active region, the SDO HMI observations with great spatial resolution and cadence helped us a lot in this. This is a particularly eruptive active region, 1158 in February 2011. What you can see here is the relative helicity calculated by this method and the free energy, and you see them here with respect to the evolution in radio waves, and this shows pretty much the triggering of flares and eruptions in general in this active region. This in particular was an X-class flare. This red line that you see over here is the onset of an X-class flare. And then we did something more in the statistical aspect. We took many active regions, not only from HMI, many different instances of active region magnetograms, vector magnetograms that is. We calculated helicity and free energy, and we put them into a diagram correlating the budget of the absolute value of the helicity with respect to the free energy. And we came up with a rather monotonic scaling between these two physical parameters, and we were able to quantify this scaling. And that was interesting. You have about 160 magnetograms included in this diagram over here. But we thought that was interesting because you can, in essence, correlate between the two, not in an exchangeable way, because helicity has a sign property as well. But nonetheless, it's better than nothing that you can correlate between these two quantities. But we aimed to validate this kind of scaling. So what you can see in here on your left is the validation effort that we did on both active regions and the quiet sun. We took some quiet sun patterns over here. It's interesting that you can discuss, you can say a lot about this diagram. You can see, for example, that you have a rather smooth, continuous progression in terms of energy when you go from active regions to the quiet sun, but you have a step change in helicity. And this, we believe, is due to the sign property of helicity. You have active regions that have a consistent, be it a left-handed or a right-handed helicity, and you have quiet sun, which is way more incoherent, having both senses of helicity in there. So algebraically speaking, your magnitude of helicity is going to go closer to zero. And then you have even 3D magnetohydrodynamical models that we have in here. Incidentally, they give the similar values to the quiet sun because you have smaller fields in there, but nonetheless, what we wanted to make clear from here is that the scaling, namely the power law index of the correlation between free energy and helicity, has been preserved. In another test that was undertaken by Slava Sadikov, then at the New Jersey Institute of Technology, tried almost 1,250 different active regions from SDO HMI. What you can see over here in the purple line is the nominal scaling that we recovered in the 2012 paper with Kostas Georgiou. This black line over here is the scaling over this expanded sample of active regions, and the red symbols over here correspond to flaring and eruptive active regions. So that was a pretty strong test, we thought, that this scaling is there and it works not only in active regions, but also in the quiet sun, and also in 3D MHD simulations in which we did not have any need to calculate helicity via the discretized formulas, but we just went ahead and tried the classical volume integral of magnetic helicity and free energy. So that we thought was a pretty solid result. So we have helicity, we have ways to calculate this helicity, and we can go ahead and use the and exploit, take advantage of the helicity conservation property that we have. So if you have a CME that's coming out and carries helicity, then you can apply a given Flagshop model because we know that CMEs are Flagshops, most of them at least. What you have in a Flagshop is that you have a structure in which you have a relatively untwisted core axis with a lot more twisted periphery that is, winding around this axis. That's a Flagshop, at least the way solar physicists are referring to it. And you have different Flagshop models. Here you see one of the simplest ones, the one that was proposed by Lundquist back in 1950, I think, in which case you can relate, as per the work of Dassault and Demoulin, Pascal Demoulin, you can relate the helicity with different Flagshop properties. And also, importantly, the axial magnetic field of the CME. And then you have data-driven modeling forward modeling by Ternesian, for example, that came out with Flagshop fittings of CMEs, real CMEs coming out of the sun. So you can do this kind of thing, and you can calculate what also the CME and heliophysics community in general call the CME BZ, which is nothing but the axial magnetic field strength of a Flagshop CME that is coming out in the heliosphere. So we did this kind of analysis. We used this simple Lundquist Flagshop model, and we try to calculate what do we expect in terms of Monte Carlo modeling at 10 solar radii away. So we have two distributions here in a work with Spiros. We have the distribution of BZ coming out of so-called quiescent active regions with weaker magnetic fields. And in the blue histogram here, we have eruptive active regions with stronger magnetic field. And over here, we have just a few observations of magnetic field measurements beyond the solar limb. And you can see that we are not that far off because these measurements were more or less quiescent structural measurements. So they align better with this histogram over here that came out, as I said, using Monte Carlo modeling. And then we said, how do we propagate this structure out in the sun, in the heliosphere from the sun, excuse me. And in this respect, we thought, based also on a good number of works in the literature, that a self-similar expansion of this structure that can be modeled in this respect, having the near sun distance of the CME from the sun, the distance somewhere in the heliosphere, the BZ of the near sun CME and the BZ of the ICME at this distance related by a power law radial fall-off thing. And then we used a Landquist Flagshop again, and we tried to compare with near Earth CME measurements at L1, Lagrangian point. I think it was like 42 events that we tried. And what we have here is the best value of this radial power law fall-off index, which is about 1.6, so minus 1.6 over here, that manages to give us a pretty high correlation between the observations for about 60% of our data over here. So we thought that was another good result based on the Landquist Flagshop though, and we tested many more Flagshops, and we ended up with something that was not that far off. In this case, we had the best correlation between observations and our modeling at a index of 1.9 or minus 1.9 here. So something between 1.6 and 1.9 helps for the heliosphere, we thought. Then we had some predictions of CME or ICME-BZ at geospace, which are not far from the observations. What you see over here is these values with respect to different values of the index. And as you can see, between 1.5 and 1.9, we ended up with field values of the order 10 to the 40 nanotesla, which are reasonable indeed. And then we try to do some fun tests, such as this one, for example, in which case we have the magnetosphere, the magnetopause distance on the left ordinate, and we have the CME, the ICME-BZ on the right ordinate, and this is Earth, 1 AU, and we try to see, based on the Earth's magnetic field that we know, it's 0.33 Gauss, what would happen if we have a superflare of a Carnot scale. Superflare meaning we have the flare energy, we calculate from the energy helicity diagram the corresponding CME helicity content, we use a Flagshop model, we propagate it, we find the BZ, and we see how far the planetary Earth's magnetosphere in this case would be compressed, right? So here is a superflare, here is a superflare of 10 to the 34 ergs. Right here, you end up with a plasma pose distance which is below 5 Earth's radii out of an unperturbed magnetopause standoff distance at 12 RF. So even though you have a substantial compression in here, you see that you do not go beyond the 2 planetary radii that would mean atmospheric erosion. So Earth is safe in this respect. This is for a power law index of the radial fall-off of 1.6. We gave it a softer one at 1.9. At the same energy, you have a magnetopause distance, a standoff distance of the order 6.5 Earth radii, so indeed Earth is safe. Even if we have an unrealistic flare energy from the sun, which is 4 to 5 orders of magnitude based on what we observe today, 10 to the 36, we would be at less or a bit more than 3 planetary radii from Earth. So Earth would not lose atmosphere in this respect, simply because it has a pretty healthy magnetic field, as you can see in here. What happens with Mars, though? With Mars, we try to take some estimates of the magnetic field, which is so much weaker than Earth. And this is not even an equatorial field. I mean, it's much more disorganized, but nonetheless, we thought that these values are equatorial values, and we ran at 1.524 AU 3 different scenarios in terms of propagation of the same event, flare of 10 to the 34 ergs. And what you can see over here is that in one case you have you have a magnetopause distance at 1.4 planetary radii, with the threshold being 2. In the other case, which is the nominal value for the power law index, you are a bit more than 2 planetary radii. In the soft kind of thing, you are again, you are above 2, so you are safe over here. But in these two scenarios, you're going to lose atmosphere because of that. So we thought that this was a quantitative kind of confirmation of MAVEN mission results, that Mars is going to be losing atmosphere because of the weak magnetic field that it has, that's going to be compressed beyond the threshold by relentless continuing solar magnetic activity. Well, there are some more results, like this gloomy result by Gira back in 2014, in which case they had the Carrington class event, but they did not take into account only the magnetic pressure, they also took account of the ram pressure, and they ended up with an Earth's compression which is slightly above the threshold of 2 solar radii. So again, minimal atmospheric erosion, but with an immense ram pressure for the CME on top of the magnetic pressure. So that I thought was interesting to show as well. We did this for the heliosphere. Moving then into the astrospheres, what we do is that we can use the scaling from the sun, because this is what we have. So if stars follow a different scaling, that's as good as we can do. We use this kind of thing for the this value for the power law index, and we try to put different exoplanets, confirmed exoplanets, on a diagram that has to do with the flare energy and helicity based on this formula, and the exoplanet distance from its host star. And what you see here is Kepler 438b and Proxima b. We have no clue about their magnetic fields, so we took a pretty strong terrestrial magnetic field as the equatorial magnetic field of both planets. And what you see in color scale is the magnetopause size, the standoff distance. The black areas are the areas that are within the atmospheric erosion kind of thing, territory. And you can see that both exoplanets over here, even with a strong magnetic field, simply because they suffer significant flares from the stars, and these are confirmed flare energies, bolometric flare energies coming from these stars. They are into the territory of losing atmosphere because of this. Here we have different scenarios. This is again the Earth's magnetic field. This is 25% of the Earth's magnetic field, and this is 6% of the Earth's magnetic field. And you can see that the weaker the field, the more deeply these exoplanets go into atmospheric erosion territory. So in terms of the Trappist system, that was a relatively recent sensation. It made international headlines. We were talking about 7 terrestrial exoplanets very close to their dwarf stars, and we also have observed flare energies. This would mean in the frame of this test that we are looking into this particular range of the spectrum. So again, into a region that would be fairly close to atmospheric erosion, tentatively speaking. But then we try to be a bit more specific. This is the work with Evangelia, in which case we said, listen, we have an additional constraint if we assume that an exoplanet is tidally locked. Because in this case, you end up with a constraint about the spin angular velocity of this planet, simply because it's going to be the same with the orbital period around the orbital velocity around its star. Okay, and in this case, you can use different recipes for the magnetic moment that's going to give you the equatorial magnetic field of a planet at a certain standoff distance. And we went on to find what is the best case scenario in this respect. If you assume that you have a planet, an exoplanet with confirmed orbital characteristics. What's the best case scenario here? So we have this is a terrestrial planet in essence. So we use a density of the core, the spin, angular velocity, we use the radius of the core and the electrical conductivity. So in this respect, we might come up with a knowledge or an expectation value at least for the equatorial planetary magnetic field. So here are several exoplanets over here. What you see is the conventional habitability zone over here, and what you see in the dust curves is actually the inner boundary of tidal locking and the outer boundary of tidal locking. So we expect planets to be possibly tidally locked in here, likely tidally locked in here, and unlikely tidally locked in here. And we have several named exoplanets, Kepler 438b or the Proxima b that I mentioned before, and the Trappist system. So we came up with the requirements for the equatorial magnetic field by assuming equipartition between the CME magnetic pressure at the threshold of 2 planetary radii, and this gave us these equatorial constraints. And this gave us the best case planetary magnetic field scenario. So if you take the ratio, we have a so-called atmosphere sustainability constraint, magnetic atmosphere sustainability constraint, by simply combining these two values, the numerator being the conditions that the requirement that the planetary magnetic field must fulfill, and the denominator meaning the actual magnetic field of the planet. So if you have R being larger than 1, then you have an unlikely atmosphere. If you have R being smaller than 1, then you have an atmosphere likely, because in this respect, your planetary magnetic field extends beyond the requirements for the equipartition at 2 planetary radii. Okay? So here are some quick results. We have 6 exoplanets. We have 4 from the Trappist system. We have Proxima Centauri, and we have Kepler 438b. And here is the R value. And you can see that it is way above 1 in most cases, except perhaps in terms of Kepler 438b. Let me show you again. This is where Kepler 438b is, so it's farther beyond, and that apparently closer, farther away from the host star. So what you see over here in blue is areas in which R should be smaller than 1. What you see in red or reddish are areas in which R should be larger than 1. And you can see that both Proxima b and the Trappist system is far away from these blue regions, whereas Kepler 438b is closer. This is just a value. For all 6 cases of apparently tidally locked exoplanets, we ended up saying that we do not expect atmospheres to be likely. But we try to do some uncertainty analysis over here. What did we do? We calculated the value of the self-similar power law index for the propagation based on this R equals 1, which is equipartition at 2 planetary radii, and an uncertainty of this value. So if this is so far away from this nominal value of 1.6, 1.9, then the result is robust based on its uncertainty. If it is closer to it, so if you take this uncertainty, then you have the values of 1.6 to 1.9 in between that range, then the result is something that we give but is not necessarily robust. So in 5 out of 6 cases for Proxima b and the Trappist exoplanets, we have a robust result because we are so far away from 1.6 or 1.9. You can see over here 3.48, it has to be extremely soft, or 4.95. So even with the error bars, you are far away from 1.6 or 1.9. But not for Kepler 438b, which is, okay, a bit softer, But given the uncertainty, the values of 1.6 or 1.9 are within this range. So the result here is not robust, but it seems robust in 5 out of 6 cases. And this is only the magnetic pressure, mind you. If you add thermal pressure or RAM pressure, then the results are going to be even worse. So in terms of potential enhancements, I'm closing with these remarks here. You have a very interesting study that came out by Sofia Moscow. And in this study back in 2019, they were able to correlate the X-ray energy of flares with the CME kinetic energy. That would conceivably mean that the study that I showed you before with this study can be combined by adding a RAM pressure or a maximum likelihood or an expected RAM pressure in there, in which case you end up with an atmosphere sustainability constraint that is magnetic plus RAM, right? And it generalizes to something like that over here, which you can calculate and have a better educated value of whether you expect an atmosphere or not. Uncertainty is going to be a bit more tricky in this respect, but at least you have an estimated value of R that is more educated than having just the magnetic pressure. And then, as you are all aware, because this is an excellent work that is coming out from your lab by Astrid and company, you can find CME, stellar CME candidates by dimming, by coronal dimming of stars. And I enjoyed reading this work. But here's an idea, a possible idea. You have the dimming over here, and you have the flare region over there. So conceivably speaking, you can correlate dimming with flare energy. The details have to be worked out, but I don't see why it could not be done. Correlating this with the flare energy, you have also an estimate of the mass. I mean, at some point in the paper, it says that it was found that in some cases, the half of the corona of the star could be blown away by the CME. That's amazing. And you can have an estimate of the coronal mass, so you can end up with an estimate of the kinetic energy of the CME as well. But also, because you're using dimming, you might be able to say something about the thermal properties. So combining this with what I have said already, you have the magnetic plus RAM plus thermal atmospheric sustainability constraint that would generalize like that. And in principle, it can be also calculated. So, in my conclusions here, what did I talk about? I talked about a first principle fundamental physics approach to estimate the magnetic forcing from the sun in a way that can be extended to stars, to only take a minimal amount of information so that it can be relatively easily applied to stars as well. So it looks like that this analysis has corroborated results of the MAVEN mission, that the Martian atmosphere might have been lost due to extensive, consistent, intense solar magnetic activity over a interval of billions of years. Okay. Then we looked into stars and how these can be enriching our knowledge about the stellar space weather in this respect and what it can do to the exoplanets. And we further ended up saying that tidal locking here might be a showstopper for the atmosphere sustainability of terrestrial planets. At least we did not touch giant or gas planets, gas giants or anything like that, because we would have no clue about how to calculate the equatorial magnetic field of these planetary bodies. But nonetheless, for terrestrial planets, which is our own idea of where to look for habitability, perhaps, then tidal locking might be a showstopper, simply because it leads to much weaker magnetic fields to be able to possibly sustain the pressure effects by stellar ICMEs. So in this respect, this analysis is a first step that might even lead possibly to a rewriting of planetary habitability criteria but also it can be further expanded, at least in my mind, by taking into account different angles, such as kinetic energy of CMEs and perhaps thermal properties of CMEs to reach better educated values. So all in all, this is my diagram here that shows again the habitability zone highlighted in purple, and it shows the two regions of tidal locking. So if the results that I just presented to you have some connection to reality, then this is probably we should be looking at. We should be looking at this zone of the habitability that is likely tidal unlocked or quite likely tidal unlocked, and be looking into these exoplanets, terrestrial exoplanets, for habitability, for atmosphere sustainability first and habitability second. So this region over here might possibly be out of question. So all in all, it looks like that we have a bit more of a way to go in order to be able to assert that we have such idyllic exostar sets coming out from terrestrial planets in other stellar systems, such as this artist conception of the Trappist, one of the Trappist terrestrial planets in the habitability zone. We might be a bit farther away from that. Thanks a lot. And I'm open for questions.
Thanks, Manolis, for this very interesting talk. I'm sure there are many questions because you covered a lot of interesting different subjects, I would say. So please, if you would like to pose a question, either put it in the chat or unmute yourself and ask Manolis directly. And I especially encourage students to raise some questions.
May I ask a question?
Sure, please go ahead.
Okay, thank you very much for this very interesting talk. You have shown the balance equation, the magnetic pressure on the one side from the CME and the magnetic pressure of the planet, the other side. I have missed the contribution of the Chapman-Ferraro currents on the surface boundary. Can you comment on that? Because this contribution is very strong.
Right. So you mean surface currents on the planet? Is this what you mean?
Surface on the magnetobars.
Oh, yes. Okay. So indeed, we could go ahead and do that, and it is a strong and non-negligible contribution at least. But based on some preliminary testing, we thought that the magnetic pressure would be the parameter to look at in this respect as the dominant parameter. So, and we try to keep the analysis simple, so it might well be included into future steps. But for the time being, we thought that the simplest possible approach that would give some results of interest would be by taking into account the magnetic pressure alone in this respect.
Okay, thank you.
Thank you.
Thank you.
Questions? Nobody is daring to ask questions. Come on. I know it's almost summer vacation, but...
Yeah, feel free. This means that either everything was clear or nothing was clear. And that could be bad.
Okay, maybe to make it more easy, I will stop recording now so that there are no... the questions are not recorded.